A join in SQL is a way of putting two sets of data together, just like you would combine two groups of children playing together. In set theory, you have two sets A and B. Inner join equals a intersect B, the intersection the children who are in both groups. Left outer join equals a intersect B union a minus B. You keep everybody from the left set A and add the matching ones from the right. The ones that have no match get a placeholder null. Right outer join equals a intersect B union B minus A, the mirror image of the left join keeping all of the right set. Full outer join equals a intersect B union a minus B union B minus A, everyone from both sets with nulls where there is no partner. These definitions work no matter how the tables are stored. They are pure mathematical concepts that the DBMS translates into rows of a result table. An inner join works like finding the common friends between two kids. Imagine table A lists every child who likes pizza and table B lists every child who likes ice cream. An inner join on the child's name returns only those children who appear in both lists, the ones who love both pizza and ice cream. Typical use cases. Matching orders to customers only orders that have a real customer. Getting employees together with the department they belong to, but only if the department exists. Performance tip: because the DBMS only needs rows that match, it can use indexes to quickly locate matching keys. If both sides have an index on the join column, the engine may choose a hash join, build a hash table of the smaller side, or a merge join, sort both sides and walk them together. The cost is roughly O(n plus m), where n and m are the row counts of the two tables plus the cost of building any needed indexes. Explanation: a left outer join is like a teacher keeping a list of all students, the left table, and writing down the sports each student plays from another list, the right table. If a student does not play any sport, the teacher still keeps the student's name but writes nothing null in the sport column. Mechanics: 1. Find all matching rows the same as an inner join. 2. Add every row from the left table that had no match, filling the right side columns with null. Null handling. Null means no information. It is not the same as an empty string or zero. When you filter after a left join, be careful. Where right column greater than 10 will remove the null rows, turning the outer join into an inner join. Use where right column is null or right column greater than 10 if you want to keep the unmatched rows. Practical scenario: list all customers and show their latest order, even if some customers have never bought anything yet. Show every product and the quantity sold this month, with null or zero for products that sold nothing. A right outer join does the same work as a left join but starts from the right table. Picture two circles again. The right circle is kept whole and the left circle is added only where it overlaps. Because SQL is symmetric, you can always rewrite a right join as a left join by swapping the table order. Some people prefer right joins when the logical primary data lives on the right side of the query for readability. When is it preferable? When you're joining a small lookup table right to a large fact table left, and you want the query to read naturally as show every lookup value and any matching facts. In legacy code where the query was originally written with a right join and refactoring would be risky. Keeping the right join avoids accidental semantic changes. Performance is identical to a left join. The optimizer treats them the same after it swaps the tables internally. A full outer join is like putting together two guest lists for two parties, and inviting everyone even if some people were only invited to one party. All rows that match on the join key, the overlap. All rows that exist only in the left table with nulls for the right columns. All rows that exist only in the right table with nulls for the left columns. Construction alternatives. Some databases such as PostgreSQL, SQL Server, Oracle support full outer join directly. Others such as MySQL prior to 8.0 do not. You can simulate it with a union of a left join and a right join. Select all from a left join B on a .id equals B.id union. All select all from a right join B on a .id equals B.id where a .id is null. Keep only rows that came only from B. Constraints. Union all version can double count rows that match on both sides if you forget the where a .id is null filter. Full outer joins can be expensive because the optimizer may need to materialize both tables. especially when neither side has a suitable index. Some NoSQL style systems simply do not implement full outer joins at all. You must perform two separate queries and stitch the results in application code. Choosing the right join type is like picking the best tool from a toolbox. The decision matrix looks at three main factors. Cardinality, how many rows each side produces. If the left side has many more rows than the right, keep the left as the preserved side left join. If the right side is larger, consider right join or rewrite as left join with swapped tables. Use left when left is primary data, use right when right is primary. Data distribution, how many matches per key. One-to-one or many-to-one implies inner join is cheap. Many-to-many implies you may get a blow-up in rows. Consider filtering before the join or using a semi-join exists. Use full only when you truly need rows from both sides, otherwise inner or left or right. Desired result. Do you need all rows from one side even when there is no match, arrow outer join? Do you only need rows that match, arrow inner join? Choose based on the business question, for example, show every customer becomes left, show every order becomes right, show all customers and orders becomes full. The matrix helps you ask, do I need unmatched rows? If no, go inner. If yes, decide which side to preserve, then check performance, indexes, expected row count. When the DBMS builds an execution plan, it decides how to fetch and combine rows. Imagine three common strategies. Nested loop, join like a teacher checking every student outer loop against every sports list inner loop. Works well when the outer table is small or when there is an index on the inner join key. Cost approximately O of n times log m if the inner side uses an index. Hash join, the engine builds a hash table of the smaller input like writing all student names on sticky notes. Then it scans the larger input and looks up each name in the hash table. Cost approximately O of n plus m and works well for large unsorted Merge join, both inputs are sorted on the join key like two ordered decks of cards. The engine walks them together, advancing the pointer with the smaller key. Cost approximately O of n plus m, but requires both sides to be sorted or have an index that provides ordering. Index usage, if a column used in the join has a B-tree index, the optimizer can use an index seek fast lookup instead of a full table scan. Composite indexes, multi-column can cover the join key and other needed columns, eliminating extra lookups. Cost estimation, the planner assigns a numeric cost based on estimated I/O pages read CPU for hash building and memory needed. It picks the plan with the lowest total cost. Understanding the cost helps you rewrite queries, adding an index filtering early to push the optimizer toward a cheaper plan. Duplicates can appear after a join because each row on one side can match many rows on the other side, a many-to-many relationship. Think of two classes. Class A has 3 students named Alex, and Class B has 2 projects titled Science. An inner join on the name Alex will create 3 times 2 equals 6 rows, every Alex paired with every science project. Use distinct removes exact duplicate rows, but can be expensive because it forces a sort. Aggregate before joining, summarize one side first. For example, select student ID, count star as count from grades group by student ID, then join the aggregated result. Join on a primary key, ensure at least one side is a key unique, so each row can match at most one row on that side, preventing blow up. Semijoin exists or in, when you only need to know whether a match exists, not the matched rows themselves. Use where exists, select one from B where b.id equals a .id. This returns each a row at most once. Across all join types, the cardinality of the result set can be described mathematically. Inner, the size of a intersect B. Left, the size of A. Right, the size of B. Full, the size of A plus the size of B minus the size of a intersect B. If duplicates exist, replace the set sizes with multi-set bag counts, where the result size equals the sum over each join key of count A of key times count B of key for inner joins, plus the unmatched counts for outer joins. Understanding this helps you predict result set size and decide whether you need additional group by or distinct to keep numbers manageable.